Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Computer and Information Sciences, SOCIS, Master's Degree Programs, Master of Computer Applications, MCA-NU, Semester I MCS-212 Discrete Mathematics, Block-1 Elementary Logic, Unit-1 Propositional Calculus. 1.0 INTRODUCTION. According to the theory of evolution, human beings have evolved from the lower species over many millennia. The chief asset that made humans superior to their ancestors was the ability to reason. How well this ability has been used for scientific and technological development is common knowledge. But no systematic study of logical reasoning seems to have been done for a long time. The first such study that has been found is by Greek philosopher Aristotle, 384-322 B.C. in a modified form. This type of logic seems to have been taught through the Middle Ages. Then came a major development in the study of logic, its formalization in terms of mathematics. It was mainly Leibniz, 1646-1716, and George Boole, 1815-1864, who seriously studied and developed this theory, called symbolic logic. It is the basics of this theory that we aim to introduce you to in this unit and the next one. In the introduction to the block you have read about what symbolic logic is. Using it, we can formalize our arguments and logical reasoning in a manner that can easily show if the reasoning is valid, or is a fallacy. How we symbolize the reasoning is what is presented in this unit. More precisely, in section 1.2, i.e., Sec. 1.2, in brief, we talk about what kind of sentences are acceptable in mathematical logic. We call such sentences statements or propositions. You will also see that a statement can either be true or false. Accordingly, as you will see, we will give the statement a truth value T or F. In Sec. 1.3 we begin our study of the logical relationship between propositions. This is called propositional calculus. In this we look at some ways of connecting simple propositions to obtain more complex ones. To do so, we use logical connectives like and, or. We also introduce you to other connectives like not, implies, and is implied by. At the same time we construct tables that allow us to find the truth values of the compound statement that we get. In Sec. 1.4 we consider the conditions under which two statements are the same. In such a situation we can safely replace one by the other. And finally, in Sec. 1.5, we talk about some common terminology and notation which is useful for quantifying the objects we are dealing with in a statement. It is important for you to study this unit carefully, because the other units in this block are based on it. Please be sure to do the exercises as you come to them. Only then will you be able to achieve the following objectives. 1.1 Objectives. After reading this unit, you should be able to distinguish between propositions and non-propositions. Construct the truth table of any compound proposition. Identify and use logically equivalent statements. Identify and use logical quantifiers. Let us now begin our discussion on mathematical logic. 1.2 Propositions. Consider the sentence, in 2003, the President of India was a woman. When you read this declarative sentence, you can immediately decide whether it is true or false. And so can anyone else. Also, it wouldn't happen that some people say that the statement is true and some others say that it is false. Everybody would have the same answer. So this sentence is either universally true or universally false. Similarly, an elephant weighs more than a human being is a declarative sentence, which is either true or false, but not both. In mathematical logic we call such sentences statements or propositions. On the other hand, consider the declarative sentence, women are more intelligent than men. Some people may think it is true while others may disagree. So, it is neither universally true nor universally false. Such a sentence is not acceptable as a statement or proposition in mathematical logic. Note that a proposition should be either uniformly true or uniformly false. For example, an egg has protein in it, and the Prime Minister of India has to be a man. are both propositions, the first one true and the second one false. Would you say that the following are propositions? Watch the film. How wonderful. What did you say? Actually, none of them are declarative sentences. The first one is an order, the. Second an exclamation and the third is a question. And therefore, none of them are propositions. Now for some mathematical propositions. You must have studied and created many of them while doing mathematics. Some examples are 2 plus 2 equals 4. 2 plus 2 equals 5. X plus y greater than 0 for x greater than 0 and y greater than 0. A set with n elements has 2 n subsets. Of these statements, 3 are true and 1 false. Which one? Now consider the algebraic sentence, x plus y greater than 0. Is this a proposition? Are we in a position to determine whether it is true or false? Not unless we know the values that x and y can take. For example, it is false for x equals 1, y equals minus 2 and true if x equals 1, y equals 0. Therefore, x plus y greater than 0 is not a proposition, while x plus y greater than 0 for x greater than 0, y greater than 0 is a proposition. Usually, when dealing with propositions, we shall denote them by lowercase letters like p, q, etc. So, for example, we may denote ice is always cold by p, or cos 2 theta plus sin 2 theta equals 1 for theta element of 0, 2 pi by q. We shall sometimes show this by saying p, ice is always cold, or q, cos 2 theta plus sin 2 theta equals 1 for theta element of 0, 2 pi. Now, given a proposition, we know that it is either true or false, but not both. If it is true, we will allot it the truth value t. If it is false, its truth value will be f. So, for example, the truth value of sometimes, as in the context of logic circuits, see Unit 3, we will use 1 instead of t and 0 instead of f. Ice melts at 30 C is f, while that of x2 is greater than or equal to 0 for x element of R is t. Here are some exercises for you now. Let us now look at ways of connecting simple propositions to obtain compound statements. 1.3 Logical connectives. When you are talking to someone, do you use very simple sentences only? Don't you use more complicated ones which are joined by words like and, or, etc.? In the same way, most statements in mathematical logic are combinations of simpler statements joined by words and phrases like and, or, if, then, if and only if, etc. These words and phrases are called logical connectives. There are 6 such connectives, which we shall discuss one by one. 1.3.1 Disjunction. Consider the sentence, Alice or the mouse went to the market. This can be written as Alice went to the market or the mouse went to the market. So, this statement is actually made up of 2 simple statements connected by, or. We have a term for such a compound statement. Definition. The disjunction of 2 propositions P and Q is the compound statement or Q, denoted by P or Q. For example, Zarina has written a book or Singh has written a book. Is the disjunction of P and Q, where P, Zarina has written a book, and Q, Singh has written a book. Similarly, if P denotes 2 greater than 0, and Q denotes 2 less than 5, then P or Q denotes the statement 2 is greater than 0 or 2 is less than 5. Let us now look at how the truth value of P or Q depends upon the truth values of P and Q. For doing so, let us look at the example of Zarina and Singh, given above. If even one of them has written a book, then the compound statement P or Q is true. Also, if both have written books, the compound statement P or Q is again true. Thus, if the truth value of even one out of P and Q is T, then that of P or Q is T. Otherwise, the truth value of P or Q is F. This holds for any pair of propositions P and Q. To see the relation between the truth values of P, Q and P or Q easily, we put this in the form of a table, Table 1, which we call a truth table. Table 1, truth table for disjunction. How do we form this table? We consider the truth values that P can take, T or F. Now, when P is true, Q can be true or false. Similarly, when P is false, Q can be true or false. In this way, there are 4 possibilities for the compound proposition P or Q. Given any of these possibilities, we can find the truth value of P or Q. For instance, consider the third possibility, i.e., P is false and Q is true. Then, by definition, P or Q is true. In the same way, you can check that the other rows are consistent. Let us consider an example. Example 1. Obtain the truth value of the disjunction of, the earth is flat, and 3 plus 5 equals 2. Solution. Let P denote, the earth is flat, and Q denote, 3 plus 5 equals 2. Then we know that the truth values of both P and Q are F. Therefore, the truth value of P or Q is F. Try an exercise now. E4. Write down the disjunction of the following propositions, and give its truth value. 1. 2 plus 3 equals 7. 2. Radha is an engineer. We also use the term, inclusive or, for the connective we have just discussed. This is because P or Q is true even when both P and Q are true. But, what happens when we want to ensure that only one of them should be true? Then we have the following. Connective. Definition. The exclusive disjunction of two propositions P and Q is the statement. Either P is true or Q is true, but both are not true. Either P is true or Q is true, but both are not true. We denote this by P circled plus Q. So, for example, if P is 2 plus 3 equals 5, and Q the statement given in E4, then P circled plus Q is the statement, either 2 plus 3 equals 5 or Radha is an engineer. This will be true only if Radha is not an engineer. In general, how is the truth value of P circled plus Q related to the truth values of P and Q? This is what the following exercise is about. E5. Write down the truth table for circled plus. Remember that P circled plus Q is not true if both P and Q are true. Now let us look at the logical analog of the coordinating conjunction, and 1.3.2 conjunction. As in ordinary language, we use and to combine simple propositions to make compound ones. For instance, 1 plus 4 does not equal 5 and Prof. Rao teaches chemistry is formed by joining 1 plus 4 does not equal 5 and Prof. Rao teaches chemistry by and. Let us define the formal terminology for such a compound statement. Definition. We call the compound statement, P and Q, the conjunction of the statements P and Q. We denote this by P and Q. For instance, 3 plus 1 does not equal 7 and 2 greater than 0, is the conjunction of 3 plus 1 does not equal 7, and 2 greater than 0. Similarly, 2 plus 1 equals 3 and 3 equals 5 feet is the conjunction of 2 plus 1 equals 3, and 3 equals 5. Now, when would P and Q be true? Do you agree that this could happen only when both P and Q are true, and not otherwise? For instance, 2 plus 1 equals 3 and 3 equals 5 feet is not true, because 3 equals 5 feet is false. So, the truth table for conjunction would be as in Table 2. Table 2. Truth table for conjunction. Look at the screen. To see how we can use the truth table above, consider an example. Example 2. Obtain the truth value of the conjunction of 2 divided by 5 equals 1, and Padma is in Bangalore. Solution. Let P, 2 divided by 5 equals 1, and Q, Padma is in Bangalore. Then the truth value of P is F. Therefore, from Table 3 you will find that the truth value of P and Q is F. Why don't you try an exercise now? E6. Give the set of those real numbers x for which the truth value of P and Q is t, where P, x greater than minus 2, and Q, x plus 3 does not equal 7. If you look at tables 1 and 2, do you see a relationship between the truth values in their last columns? You would be able to formalize this relationship after studying the next connective. 1.3.3 Negation. You must have come across young children who, when asked to do something, go ahead and do exactly the opposite. Or, when asked if they would like to eat, say rice. and curry will say no, the negation of yes. Now, if P denotes the statement, I will eat rice, how can we denote, I will not eat rice? Let us define the connective that will help us do so. Definition. The negation of a proposition P is not P, denoted by tilde P. For example, if P is, Dolly is at the study center, then tilde P is, Dolly is not at the study cent. Similarly, if P is, no person can live without oxygen, tilde P is, at least one person can live without oxygen. Now, regarding the truth value of tilde P, you would agree that it would be T if that of P is F, and vice versa. Keeping this in mind, you can try the following exercises. E7. Write down tilde P, where P is 1, 0 to 5 does not equal 5. 2. N greater than 2 for every n element of n. 3. Most Indian children study till class 5. E8. Write down the truth table of negation. Let us now discuss the conditional connectives, representing if, then, and if. And only if. 1.3.4 Conditional connectives. Consider the proposition, if Aisha gets 75% or more in the examination, then she will get an A grade for the course. We can write this statement as, if P and Q, where P, Aisha gets 75% or more in the examination, and Q, Aisha will get an A grade for the course. This compound statement is an example of the implication of Q by P. Definition. Given any two propositions P and Q, we denote the statement, if P, then Q, by P right pointing arrow Q. We also read this as, P implies Q, or P is sufficient for Q, or P only if Q. We also call P the hypothesis and Q the conclusion. Further, a statement of the form P right pointing arrow Q is called a conditional statement or a conditional proposition. So, for example, in the conditional proposition, if M is in Z, then M belongs to Q. The hypothesis is M element of Z, and the conclusion is M element of Q. Mathematically, we can write the statement as M element of Z right pointing arrow M element of Q. Let us analyze the statement P right pointing arrow Q for its truth value. Do you agree with the truth table we've given below, table 3? You may like to check it out while keeping an example from your surroundings in mind. Table 3, truth table for implication. Look at the screen. You may wonder about the third row in table 3. But, consider the example, 3 less than 0 right pointing arrow. 5 greater than 0. Here the conclusion is true regardless of what the hypothesis is. And, therefore, the conditional statement remains true. In such a situation we say that the conclusion is vacuously true. Why don't you try this exercise now? E9. Write down the proposition corresponding to P right pointing arrow Q, and determine the values of X for which it is false, where P, X plus Y equals XY where X, Y element of R. Q, X0 for every X element of Z. Now, consider the implication, if Jahanara goes to Baroda, then she doesn't participate in the conference at Delhi. What would its converse be? To find it, the following definition may be useful. Definition. The converse of P right pointing arrow Q is Q right pointing arrow P. In this case we also say, P is necessary for Q, or P if Q. So, in the example above, the converse of the statement would be, if Jahanara doesn't participate in the conference at Delhi, then she goes to Baroda. This means that Jahanara's non-participation in the conference at Delhi is necessary for her going to Baroda. Now, what happens when we combine an implication and its converse? To show P right pointing arrow Q and Q right pointing arrow P, we introduce a shorter notation. Definition. Let P and Q be two propositions. The compound statement P right pointing arrow Q and Q right pointing arrow P is the biconditional of P and Q. We denote it by P left right arrow Q, and read it as P if and only Q. We usually shorten if and only if to IFF. We also say that P implies and is implied by Q, or P is necessary and sufficient for Q. For example, Sudha will gain weight if and only if she eats regularly. Means that Sudha will gain weight if she eats regularly and Sudha will eat regularly if she gains weight. One point that may come to your mind here is whether there's any difference in the two statements P left right arrow Q and Q left right arrow P. When you study Sec. 1.4 you will realize why they are interchangeable. Let us now consider the truth table of the biconditional, i.e., of the two-way implication. To obtain its truth values, we need to use tables 2 and 3, as you will see in table 4. This is because, to find the value of P right pointing arrow Q, and Q right pointing arrow P, we need to know the values of each of the simpler statements involved. Table 4, truth table for two-way implication. Look at the screen. As you can see from the last column of the table, and from your own experience, P left right arrow Q is true only when both P and Q are true or both P and Q are false. In other words, P left right arrow Q is true only when P and Q have the same truth values. Thus, for example, Parimala as in America IFF 2 plus 3 equals 5 feet is true only if Parimala as in America is true. Here are some related exercises. E10. For each of the following compound statements, first identify the simple propositions P, Q, R, etc. that are combined to make it. Then write it in symbols using the connectives and give its truth value. 1. If triangle ABC is equilateral, then it is isosceles. 2. A and B are integers if and only if AB is a rational number. 3. If Raza has 5 glasses of water and Sudha has 4 cups of tea, then Shyam will not pass the math examination. 4. Mariam is in class 1 or in class 2. E11. Write down two propositions P and Q for which Q right pointing arrow P is true but P left right arrow Q is false. Now, how would you determine the truth value of a proposition which has more than one connective in it? For instance, does tilde P or Q mean tilde P or Q or tilde P or Q? We discuss some rules for this below. 1.3.5 Precedence Rule. While dealing with operations on numbers, you would have realized the need for applying the BODMAS rule. According to this rule, when calculating the value of an arithmetic expression, we first calculate the value of the bracketed portion, then apply of division, multiplication, addition and subtraction, in this order. While calculating the truth value of compound propositions involving more than one connective, we have a similar convention which tells us which connective to apply. First, why do we need such a convention? Suppose we didn't have an order of preference and want to find the truth of, say, tilde P or Q. Some of us may consider the value of tilde P or Q, and some may consider tilde P or Q. The truth values can be different in these cases. For instance, if P and Q are both true, then tilde P or Q is true, but tilde P or Q is false. So, for the purpose of unambiguity, we agree to such an order or rule. Let us see what it is. The rule of precedence, the order of preference in which the connectives are applied in a formula of propositions that has no brackets is 1. Tilde. 2. Conjunction. 3. Disjunction and OPLUS. 4. Right pointing arrow implies and left right arrow equivalent. Note that the inclusive or and exclusive or are both third in the order of preference. However, if both these appear in a statement, we first apply the leftmost one. So, for instance, in P or Q circled plus tilde P, we first apply or and then circled plus. The same applies to the implication and the biconditional, which are both fourth in the order of preference. To clearly understand how this rule works, let us consider an example. You can check that the rest of the values are as given in table 5. Note that we have 8 possibilities equals 2 cube, because there are 3 simple propositions involved here. Table 5, truth table. Look at the screen. But, are all these new ones distinct? Or are some of them the same? And, same, in what way? This is what we shall now consider. 1.4 Logical equivalence. Then you should say what you mean, the march have went on. I do. Alice hastily replied, at least I mean what I say, that's the same thing you know. Not the same thing a bit, said the Hatter. Why, you might just as well say that, I see. What I eat, is the same thing as, I eat what I see. From Alice in Wonderland. In mathematics, as in ordinary language, there can be several ways of saying the same thing. In this section we shall discuss what this means in the context of logical statements. Consider the statements, if Lala is rich, then he must own a car. And, if Lala doesn't own a car, then he is not rich. Do these statements mean the same thing? If we write the first one as P right pointing arrow Q, then the second one will be tilde Q, right pointing arrow, tilde P. How do the truth values of both these statements compare? We find out in the following table. Table 6. Look at the screen. Consider the last two columns of Table 6. You will find that P right pointing arrow Q and Q right pointing arrow tilde P have the same truth value for every choice of truth values of P and Q. When this happens, we call them equivalent statements. Definition. We call two propositions R and S logically equivalent provided they have the same truth value for every choice of truth values of simple propositions involved in them. We denote this fact by R is defined as S. So, from Table 6 we find that P right pointing arrow Q is defined as tilde Q right pointing arrow tilde P. You can also check that P left right arrow Q is defined as Q left right arrow P for any pair of propositions P and Q. As another example, consider the following equivalence that is often used in mathematics. You could also apply it to obtain statements equivalent to neither a borrower nor a lender be. The equivalence you have just seen is one of De Morgan's laws. You might have already come across these laws in your previous studies of basic mathematics. The other law due to De Morgan is similar. Tilde P and Q is defined as tilde P or tilde Q. Fig. 1. Augustus De Morgan, 1806 to 1871, was born in Madurai. In fact, there are several such laws about equivalent propositions. Some of them are the following, where, as usual, P, Q and R denote propositions. A. Double negation law. Tilde P is defined as P. B. Idempotent laws. P and P is defined as P. P or P is defined as P. C. Commutativity. P or Q is defined as Q or P. P and Q is defined as Q and P. D. Associativity. P or Q or R is defined as P or Q or R. P and Q and R is defined as P and Q and R. A. Distributivity, or Q and R, is defined as P or Q and P or R. P and Q or R is defined as P and Q or P and R. We ask you to prove these laws now. A16. Show that the laws given in A above hold true. E17. Prove that the relation of logical equivalence is an equivalence relation. E18. Check whether tilde P or Q and P right pointing arrow Q are logically equivalent. The laws given above and the equivalence you have checked in E18 are commonly used, and therefore, useful to remember. You will also be applying them in Unit 3 of this block in the context of switching circuits. C. Commutativity. P or Q is defined as Q or P. P and Q is defined as Q and P. D. Associativity. P or Q or R is defined as P or Q or R. P and Q and R is defined as P and Q and R. A. Distributivity, or Q and R, is defined as P or Q and P or R. P and Q or R is defined as P and Q or P and R. Let us now consider some prepositional formulae which are always true or always false. Take, for instance, the statement, if Bano is sleeping and Papu likes ice cream, then Bano is sleeping. You can draw up the truth table of this compound proposition and see that it is always true. This leads us to the following definition. Definition: a compound proposition that is true for all possible truth values of the simple propositions involved in it is called a tautology. Similarly, a proposition that is false for all possible truth values of the simple propositions that constitute it is called a contradiction. Why don't you try an exercise now? E19. Let T denote a tautology, i.e., a statement whose truth value is always T and F. A contradiction. Then, for any statement P, show that 1. P or T is defined as T. 2. P and T is defined as P. 3. P or F is defined as P. 4. P and F is defined as F. The laws of logical equivalence can also be used to prove some other logical equivalences, without using truth tables. Let us consider an example. You may now like to try the following exercises on the same lines. E20. Use the laws given in this section to show that tilde P and Q, and P or Q, is defined as P. E21. Write down the statement, if it is raining and if rain implies that no one can go to see a film, then no one can go to see a film. As a compound proposition, show that this proposition is a tautology by using the properties of logical equivalence. E22. Give an example, with justification, of a compound proposition that is neither a tautology nor a contradiction. Let us now consider proposition-valued functions. 1.5 Logical quantifiers. In Sec. 1.2, you read that a sentence like, she has gone to Patna, is not a proposition, unless who, she, is clearly specified. Similarly, x greater than 5 feet is not a proposition unless we know the values of x that we are considering. Such sentences are examples of propositional functions. Definition: a propositional function, or a predicate, in a variable x is a sentence P, x, involving x that becomes a proposition when we give x a definite value from the set of values it can take. We usually denote such functions by P, x, q, x, etc. The set of values x can take is called the universe of discourse. So, if P, x, is x greater than 5, then P, x, is not a proposition. But when we give x particular values, say x equals 6 or x equals 0, then we get propositions. Here, P, 6, is a true proposition, and P, 0, is a false proposition. So, if P, x, is x greater than 5, then P, x, is not a proposition. But when we give x particular values, say x equals 6 or x equals 0, then we get propositions. Here, P, 6, is a true proposition, and P, 0, is a false proposition. Similarly, if Q, x, is x has gone to Patna, then replacing x by Taj Mahal gives us a false proposition. Note that a predicate is usually not a proposition. But, of course, every proposition is a prepositional function in the same way that every real number is a real valued function, namely, the constant function. There is called the existential quantifier. Now, can all sentences be written in symbolic form by using only the logical connectives? What about sentences like, x is prime and x plus 1 is prime for some x? How would you symbolize the phrase, for some x, which we can rephrase as, there exists an x? You must have come across this term often while studying mathematics. We use the symbol, there is, to denote this quantifier, there exists. The way we use it is, for instance, to rewrite, there is at least one child in the class, as, there is x in U, P, x, where P, x, is the sentence, x is in the class, and U is the set of all children. Now suppose we take the negative of the proposition we have just stated. Wouldn't it be, there is no child in the class? We could symbolize this as, for all x in U, Q, x. Where x ranges over all children and Q, x, denotes the sentence, x is not in the class. I.e., Q, x, is defined as tilde P, x. We have a mathematical symbol for the quantifier, for all, which is, for all. So the proposition above can be written as, for all x in U, Q, x, or, Q, x, for all x in U. For all is called the universal quantifier. We often use both quantifiers together, as in the statement called Bertrand's postulate. For all n in n1, there is x in n. X is a prime number and n less than x less than 2n. In words, this is, for every integer n greater than 1 there is a prime number lying strictly between n and 2n. As you have already read in the example of a child in the class. For all x in U, P, x, is logically equivalent to tilde, there is x in U, tilde P, x. Therefore, tilde, for all x in U, P, x, is defined as tilde tilde, there is x in U, tilde P, x, is defined as, there is x in U, tilde P, x. This is one of the rules for negation that relate for all and there is. The two rules are, tilde, for all x in U, P, x, is defined as, there is x in U, tilde P, x, and tilde, there is x in U, P, x, is defined as, for all x in U, tilde P, x. Where U is the set of values that x can take. Now, consider the proposition. There is a criminal who has committed every crime. We could write this in symbols as, there is C in A, for all x in B, C has committed x. Where, of course, A is the set of criminals and B is the set of crimes, determined by law. What would its negation be? It would be, tilde, there is C in A, for all x in B, C has committed x. Where, of course, A is the set of criminals and B is the set of crimes, determined by law. What would its negation be? It would be, tilde, there is C in A, for all x in B, C has committed x. Is defined as, for all C in A, tilde, for all x in B, C has committed x. Is defined as, for all C in A, there is x in B, C has not committed x. We can interpret this as, for every criminal, there is a crime that this person has not committed. These are only some examples in which the quantifiers occur singly, or together. Sometimes you may come across situations, as in E23, where you would use there's or for all. Twice or more in a statement. It is in situations like this or worse, say, for all she in U1, there is x2 element of U2, there is x3 element of U2, there is x3 element of U3, for all x4 element of U4, there is xn element of un, p. A predicate can be a function in two or more variables. Where our rule for negation comes in useful. In fact, applying it, in a trice we can say that the negation of the seemingly complicated example is, there is x1 element of U1, for all x2 element of U2, for all x3 element of U3, there is x4 element of U4, for all xn element of un, tilde p. Why don't you try some exercise now? E23. How would you present the following propositions and their negations using logical quantifiers? Also interpret the negations in words. 1. The politician can fool all the people all the time. 2. Every real number is the square of some real number. 3. There is lawyer who never tell lies. E24. Write down suitable mathematical statements that can be represented by the following symbolic propositions. Also write down their negations. What is the truth value of your propositions? 1. For all x, there is y, p. 2. There is x, there is y, for all z, p. And finally, let us look at a very useful quantifier, which is very closely linked to there is. You would need it for writing, for example, there is one and only one key that fits the desk's lock. In symbols, the symbol is there is exactly one x, which stands for there is one n. Only one x, which is the same as there is a unique x, or there is exactly one x. So, the statement above would be, there is exactly one x element of A, x fits the desk's lock, where A is the set of keys. For other examples, try and recall the statements of uniqueness in the mathematics that you've studied so far. What about, there is a unique circle that passes through three non-collinear points in a plane. How would you represent this in symbols? If x denotes a circle, and y denotes a set of three non-collinear points in a plane, then the proposition is, for all y in P, there is exactly one x element of C, x passes through y. Here C denotes the set of circles, and P the set of sets of three non-collinear points. And now, some short exercises for you. Before ending the unit, let us take a quick look at what A have covered in it. 1.6 SUMMARY. In this unit, we have considered the following points. 1. What a mathematically acceptable statement, or proposition, is. 2. The definition and use of logical connectives. Give propositions P and Q. I, their disjunction is P and Q, denoted by P or Q. E, their exclusive disjunction is either P or Q, denoted by P circled plus Q. E, their conjunction is P and Q, denoted by P and Q. IV, the negation of P is not P, denoted by tilde P. V, if P, then Q, is denoted by P right pointing arrow Q. V, P if and only if Q, is denoted by P left right arrow Q. 3. The truth tables corresponding to the 6 logical connectives. 4. Rule of precedence. In any compound statement involving more than one connective, we first apply tilde, then, and, then, or, and, circled plus, and last of all, right pointing arrow, and left right arrow. 5. The meaning and use of logical equivalence, denoted by, is defined as. 6. The following laws about equivalent propositions. Now we have come to the end of this unit. You should have tried all the exercises as you came to them. You may like to check your solutions with the ones we have given below. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.